background.
So, hello all, good afternoon. I welcome you all for the third edition of our fitness webinar series. So, it's my absolute pleasure to introduce our speaker, Professor Bikash Pal. Professor Paul is a professor at Power Systems at Imperial College London. Uh, he has received his BE degree from Jadavpur University and ME Engineering degree in Power Systems from the Indian Institute of Science, Bangalore, both from India in 1990 and 1992, respectively. He completed his PhD degree from Imperial College London as a Commonwealth Scholar in 1999. He is internationally recognized for his research in power system stability, control, and estimation. He has so far led three multinational and multi-university research collaborations between UK, China, and India in the area of renewable energy integration and control. His research is conducted in strategic partnership with ABB, Siemens, GE Grid Solutions UK, National Grid UK, and UK Power Networks. Siemens R&D collaborated with Professor Paul to develop fast power flow and volt-var control tool for their product, Spectrum Power, an advanced module for distribution management system solutions from Siemens used by many utilities worldwide. GE commissioned a sequel of projects with him to analyze and solve wind farm HVDC grid interaction problems between 2013 and 2019. Professor Paul was appointed by the prestigious United Nations Framework Convention on Climate Change, UNFCCC, as a chief technical consultant for a panel of experts for clean development mechanism. He has offered trainings in Chile, Qatar, UAE, Malaysia, and India in power system protection, stability, and control topics. He has developed and validated a prize-winning 68-bus power system model, which is now part of IEEE benchmark systems as a standard for researchers to validate their innovations in stability analysis and control design. He has so far published about 140 papers in IEEE transactions and other four books covering power system modeling, dynamics, estimation, and control. In terms of recognition, Professor Paul's research team received the President's Outstanding Research Team Award at Imperial College London in 2016. He is recognized as a Fellow of IEEE for his contributions to power system stability and control. He is also the Fellow of Chinese Society of Electrical Engineers and the IET UK. He received 2025 IEEE PES Prabha Kundur Power System Dynamics and Control Award for his technical contribution to power system control and estimation. He was elected Fellow of the Royal Academy of Engineering UK in 2023 for the impact of his contribution to the field of power engineering. He was also elected as a foreign member of Chinese Academy of Engineering and Indian National Academy of Engineering in 2025. He is an IEEE Distinguished Lecturer in Power Distribution System Estimation and Control. He was Otto Monstedt Professor at Denmark Technological University in 2019 and Mercator, Mercator Professor sponsored by German Research Foundation at the University of Duisburg Essen in 2011. He previously worked as a faculty at IIT Kanpur, India, and currently holds distinguished visiting professorship at the North China Power Electric University and Tsinghua University in China. He was the editor in chief of IEEE Transactions on Sustainable Energy between 2012 and 2017, and editor in chief of IET Generation, Transmission, and Distribution between 2005 and 2012. He was vice president, PES Publications between 2019 and 23. He is elected as the IEEE Power and Energy Society president elect for the year of 2026 and 27 for the office of the president in 2028 and 2029. Beyond his professional achievements, he is also founder of Kaja Babu Memorial Trust, an education charity in India dedicated to mentoring children from economically disadvantaged backgrounds. So please join me in welcoming Professor Bikash Pal. Thank you so much, Professor.
Oh, Shai, that was so long. You have already read my full biography. Okay. Hello, everyone. How are you doing? Are you able to see my screen?
Yes.
Okay.
Yes,
And
Professor.
you are also able to hear me.
Yes, clear.
Right. So this topic is robust volt-VAR control in power distribution. This is um, um, in collaboration with a couple of funders. But let me tell you the overview. Mainly, I'll focus on the chance constraint volt-VAR control. Why volt-VAR control problem is very important, and what are the challenge also it has in order for it to be implemented. So I'll touch upon chance constraint BBC framework, that is where we don't have, say, completely an analytical or explicit mathematical formulation. So we need to do chance constraint with many scenarios. And then we see that in the chance constraint framework, the solution is easier through, say, convex programming. But the problem that is formulated is not actually easily can be applied for convex programming. So we need to have convexification. There would be some kind of scenario enforcement algorithms, that is because we are doing chance constraint, there will be a large number of scenarios. So we'll see that if we could have some kind of scenario that we can cover, which will have a representative representation of the operating situations. And how we do that through two-stage implementation to enforce this scenario to abide by the limits. That is mainly the operating voltage limit. We will follow these results and discussion for that, and then we have a conclusions. Volt-VAR control problem, what it is, its main objective is that we operate our systems within plus minus 5%. The node voltage must be 95% on the low side to 105% on the higher side. And while we do that, we have all the feeders. So the feeders also have some the current rating. So that current rating has to be also respected, and that rating also varies from season to season. So that's this. Apart from this operational objective, there are some secondary also objectives, like minimizing the power loss, and while also we can minimize the tap positions would be changing always. So if we can make sure that we don't play with the tap as many times as possible, because when the tap is a mechanical device, if it keeps on moving, it also has its own impact on the life expectancy of the device itself. So for that, minimization and adherence to this limit, our control option available to us are switched shunt capacitor, because we are talking about distribution system context, on-load tap changing transformer, and voltage regulator set point. Then also we have the DG reactive powers, that is the distributed generator reactive power. Let me show you this one a little bit more. This voltage regulator are normally series, that when voltage drops, you bring something there. It's a kind of quadrature booster. It improves the voltage. And there is a transformer which has got the tap. The shunt capacitor, they are mainly the passive device, because if voltage is available across them, they would provide reactive power. They cannot produce the voltage on their own. That means they are more of a passive. If voltage is available across them, they can generate reactive power. Independently generating reactive power, irrespective of the voltage, is not possible, other than the power electronics option, that is STATCOM and others. And then also every distributed generator will have the reactive power generation capability, particularly when there is not enough solar resource or enough wind. The capacity of the DG can be then mixed with the reactive power, and then it provides reactive power. The advantage is that reactive power control is very fast compared to these. These are all the mechanical control, which are quite slow. Even for the capacitor, you will have the shunt, say, switched capacitor. So they are mechanical that way. So that's the arrangement of yesterday. And what is happening today and tomorrow is that this is the point where you are feeding in and distribution transformer. Then we have the uncertainty, that is having the solar PV, say, and then we have the inverter solar converter. So that is characterized by uncertainty in its P and also intermittency. So if this is uncertain, sometimes when we have more and the voltage is high, we cannot inject all of them, we can curtail. So we need to control essentially the P and Q to curtail the P when we have, say, more P. Or when we have less P also, we can again inject more Q to make sure that the voltage here is kind of sensible. That is within that range, 0.95 to 1.05. The forecast, then historically, the photovoltaics and load forecast errors have been neglected normally. But in our case, chance constant voltage control, we are including those errors into the account. And also that has been the focus of these IEEE and other standard organizations document, that distributed generator must actively participate in voltage regulation even during the fault, let alone during the operating steady state operating condition. Even during the fault, they should do. So how we can incorporate this DG reactive power support capability in the voltage regulation is what actually is also our focus. But then remember that DG reactive power is also some kind of random or stochastic, because the P that is coming from the solar, it itself is fluctuating. And sometimes we do not even know, so we normally forecast. So the forecast itself will have the uncertainty of forecast error. How you capture those uncertainty, etc., is by a statistical model. And the moment you do a statistical model, so naturally, then deterministic solution is just one solution for the base case. But for many other solutions, we really need to see how the DG control say behaves. So that's how the deterministic volt-var control minimize power loss and have the power flow model, which is node P and Q is deterministic, and then voltage is between 0.95 to 1.05. We don't include any forecast error because we know how much is going to be our P, how much is going to be our Q at every node. But as I said, we have the solar with all variation or wind with the variation. So that means if we are doing many scenarios, from the variation we can generate many scenarios, and as many scenarios are possible that we must ascertain that voltages are respected between 95 to 105%. So naturally, all of them, if we are trying, so what would be the loss? Is losses in all the scenarios, and then we take the average. That's how the objective functions change from a deterministic minimized power loss to expected power loss. Power flow model has got P and Q uncertain because of the solar injection where there is a forecast error. So that means this inequality constraint in the voltage will be transformed into a probability. The probability that the voltage at the node is within this range must be greater than something. And what is that something? That 1 minus epsilon. Okay. So that's the uncertainty in the forecast. Okay. Forecast error considered. So we are including the forecast error, and how we include that error into this, we'll see. So the technical challenge: minimize electric power loss, power flow model, probability that this is this. So This is minimized electric power loss, expected power loss is non-convex. Power flow model is also non-linear. So this non-convex and non-linear problem does not have a global solution, global optima. On top of it, the inequality constant is a probability function. It is not some kind of deterministic and mathematically well represented expression that you see in a constant optimization. You see minimize fx subject to gs. So gx, we call that as a algebraic nonlinear equations, but here we don't have that luxury because we have the probability. We don't have that just a single one. Branch flow model, let's focus on this. We have the Ohm's law between node and I and node and j. You can apply that if you have Zij. The branch power flow is then Vi conjugate, the injected current into this. That one you express for a multiple branch from a node. So Sj becomes what? The whatever comes Sij, and then whatever goes Sjk, all of them. So that's how Sjk, all of them are this that is going out, and what is coming in is Sj, that's injection, plus what is coming out from ith node. So Sij minus Zij square is what? There would be some reactive power loss in the branch. How much is that? I square into Zij. Okay. I will not say the reactive power, the complex power loss. S is Vi conjugate. So Zij square is the loss in the link. So whatever is available here is whatever is injected here minus that. So that's this plus this Sj. Okay, that's the injection, and this is the outgoing. So these two things must balance this way. Sj is what? This is this minus this, or the or also the Sij minus this plus Sj is equal to this. So then you can take that way. Okay. So this minus sign, if you take it this side, so that that's where at this point you have the continuity equation satisfied for the complex power flow. That's clear. So now this one we can take a square and then expand. Zij is Rij plus Jxij. Then you will get this. And this Sij is P plus Ji. So that square P plus Ij into P minus Ij is this plus this. So this is then Vij, this square, I conjugate into I, and then V conjugate into V. That because Si what? P plus JQ. P plus JQ into P minus JQ will give you P square plus Q square. So P minus JQ would be S conjugate. S conjugate would be V conjugate into I. So V conjugate into V is V square. I conjugate into I is I square. That's exactly this. So that's this. And then node power, you can express, separate out the real and the imaginary part that way. So now if you see this, if I define a quantity or a variable called Lij, the current that is flowing in the branch from the node I to j, that current square, because we have that, you see that current square and voltage square. So if we define two quantity, Lij is Ij square and Ui as Vi square. So then these are our new variable. And then new variable, if you put into this, the previous expression here, the new variable, then you get something like this. Pj, the jth node power injection is Pjk minus Pij, Rij, Lij. The Lij is this one into Rij. But then that is for the real power, and similarly we have for the reactive power. And remember, in that reactive power, when we are considering a PV connected node, so there that reactive power is not deterministic. So there, that is how this, and also the P, they are not deterministic. That is how the randomness, sets in. Okay. And then you have this uj as ui by this definition. Uj is ui minus 2 rij pij xij. This rij is square and x square into lij, the current. So this is the impedance square into current square, and this is rij pij and xij qij. That's the power into resistance, and this is the square of the voltage. Okay. If you see that v square by r is equal to p, v square by r is equal to p, power loss, right? So now if you multiply both sides by r, you get v square is equal to p into r. That's exactly is happening. P into r, q into x, and then this is this. And then on that you have pij and qij, the power that gets into this through this link, that is the product of lij, which is v square, and then iij, which is ui, sorry, the lij, which is iij square, and ui is equal to vi square. So that's how you could write that. If you go back, you see this is the thing. Just put this as lij and make this as u. So that's how you get this, right? P square plus this is this. Now, if you look at that, up to 3 equations, they are now linear in Pij, Qij, Lij, and Ui. All these 3 equations, you don't see any nonlinearity if your set of variables are P, Q, L, U. But it's only here you see that P square plus Q square, so it's a circular or quadratic, but there is also Lij into Ui, that's a product form. So that's the nonlinearity there. So then how we make this manageable? Rather than having equalities there, if you do something like inequality, that P plus Q must be less than this Vi. So that means you are satisfying the operating condition. So then what happens is this becomes a cone surface. So that cone surface, P square, you know that x square plus y square is equal to s square, that type of thing. So you have in this case, this is a 3-dimensional cone. Okay. So the cone of that, then moment you put anything, say less than that, so then what happens is you have this type of thing. Okay. So that is your cone. That is your cone. So when the equality that you are in the surface, but when it is less than, you are inside. Now this cone geometric structure is a convex, and if you are inside of that, any point inside of that is also convex. So that means this expression actually satisfies the convexity. So that means we have convexified it, and if we have convexified that, so naturally we can then apply some of the cone programming or convex programming tools. So this one, when you have like a square plus b square is less than ab, you can write this as 4a plus 4b minus 4a 4b, and then a minus x square plus y square is equal to less than ab. You can write this as a 2x 2y and a minus b Euclidean norm. This must be less than this. Why? You know that formula, that x a square plus b square, and then that 4ab, this this is this. So this is a plus b into a minus b here, this one. So you can easily find this expression from this to this. Okay, you can write. You see that if you make this expand again, 4pij square 4qij square plus lij minus ui square. That means lij square plus ui square minus 2 lij ui. Here, this minus, and here you have to do this this again. This is square, li square ui square 2 li ui. So then you see that you are getting this. So then take that minus into that side. So then what happens? You have 4pi square pij square plus 4qij square less than is equal to 4 into lij into ui. So 4 goes. So you get back to that same expression. Clear? So that's the second order. This is now a second order cone. So the convex constant PILIJ, they are convex constant. But one thing is this: in this Q we have that uncertainty. So that Q is not a deterministic variable. That's a random variable. And another thing is in your this U that where you have the voltage, etc., and then the I square. What you have in this Q, you will have the reactive power that is injected by the capacitor. So two things are happening. Number one, the DG reactive power that is coming has got randomness, and the reactive power that is coming from the shunt capacitor has got discreteness. So your this the Q there has got product of the binary and the continuous variable. So this is the continuous and discrete variable, because that reactive power that comes from the shunt capacitor is not a continuous function, because it has got the bank. Either you can get like 10 kVA or 20 kVA or 30 kVA, depending on size of them. But you don't get the whole spectrum. That's why there is a bilinear term and the mixed integer coming in, because these are all discrete function, and these are continuous functions. So product of the discrete and continuous function is the bilinear aspect that we can handle by big M method. So how it is happening? So let's make each of them BCJ, that jth node and bank 1, jth node, capacitor bank in the jth node, bank number 2, and then bank number of n. So let's put some arbitrary variable z j 1 to z j n. So then this is BCJ UJ. That then if I make this as z, so then I do this, say BCJ UJ as k is equal to 1 to n ZJK BCJ UJ. Now what are the ZJ? The ZJ can be either 0 or 1. That means if it is present or if it is not present. So when that, which bank is connected, okay, of that. So that means k is equal to 1 to n. If you have n number of bank in jth node of the capacitor, you will at some point of time you will only have one connected, and that means ZJK is either 0 or 1. So then what happens? We define a new quantity, this ZJ into UJ, as WJ. So that means WJ BCJ into this, because this is ZJ is a scalar quantity. You can take it to that side. So then ZJ into UJ is a new quantity, and that we call it WJK and then BCJK. So let's see what happens. In a big M method, what we do, this WJ, we have like UJ minus a large quantity, and then UJ plus a large quantity, plus a large quantity. So this is infinite, as large as possible. So U minus a large number is a minus, is tending towards minus large number, and this is tending towards a plus large number. So minus infinity to plus infinity, that way. So now let's see how this product, the discrete BCJ, WJ, and all can be, handled to be a continuous. So when ZJK is 1, that means when that capacitor is present. So then 1 minus 1 is 0. The large number gets multiplied by 0. You have UJ less than or equal to WJ, and again a large number, this is 0. So UJ is less than WJ is equal to U, and then less than UJ. So essentially, so this side UJ, that side also UJ. So that means WJ is what? It's just UJ. WJ is UJ because ZJ is equal to 1. So this is not a range, this is just a number. So that is when that capacitor is present. And when that is not present, then we go to this expression. When this is not present, that means Zj is 0. So we have Uj minus M and is less than Wj, and where Uj plus M less than this. So M being a large quantity close to infinity compared to U, so this can be minus infinity. That's why M. Okay, M into Zj, Wj, M into Zj. So that's the say this. And again, in this case, Zj is equal to 0. You see that? Minus large number is less than this. That means what? It's only possible when Wj is equal to 0. So that's the situation. So when the capacitor bank is present, that is the first formula. And when the capacitor bank is absent, then that is the last formula, this formula. And we now see this Wj is equal to 0. So when it is absent, so naturally constant need not be there. The difficult part is to find the probability density function of this expression. But easy part is we can have the probability density function of the PV forecast error. So, I mean, the voltage, etc., should be decided by how much PV is getting injected to the grid. And then Kirchhoff's current and voltage law and all the other demand, etc. So it have its own value. But we don't have that expression for the probability distribution function. So then we can then add a forecast error into that. So then it becomes, it comes from historical data, and then with that we generate what is our forecast error, and then see what is our value of Q for a particular, say, value of the random variable, and or a sample rather for one random variable. So let me little bit stretch my leg. For one random variable, you have this. Okay, let me see. Are you able to see my face? Hello? Hello?
Yes, Prof. You can see.
Yeah, if I stand, are you able to see my face? Yeah.
Yes, absolutely.
Okay. So that that means we need to have a scenario space. So how we generate the scenario? So let's we have B number of that binary discrete variable and C number of continuous variable. We need to generate n number of scenario. Ideally, it would be infinity number of scenario, but then we can get 100%. You know, the say in the chance constant, if we take infinity number of scenario and we enforce all infinite number of scenarios, then the solution would always give you the 100% confidence as well as the robustness. But in reality, it is not. So then we need to have we need to set some confidence and also the robustness bound. So we have a confidence parameter gamma and robustness parameter epsilon. What is this confidence parameter gamma? It's like if I have gamma 10 to the power of minus 6, so 1 minus 10 to the power of minus 6, that is 0.99999. So the number of scenario that we have generated, that probably, you know, if we then on that scenario, if we do this the optimization, we can say that we have covered that 99.9999% of the cases of the scenarios. Okay, and then on that there is a robustness, that is for every scenario that we talk about, that scenario has got again the uncertainty of the solar, and you know that uncertainty parameters, the how much P is the forecast error. Okay, so that uncertainty that gives us this the level of robustness. Okay, so that is epsilon level robustness. So now we formulate the problem with here that we minimize the expected power loss And we also make sure that we minimize the tap movement, the W2. So weight, we put in a weight between them. And this is an absolute number. So on the objective function, you have an expected value of the loss, and we have here the absolute value. So this actually comes as an epigraph programming. So the mechanical device, their slow speed, there is a wear and tear concern. So we objective is minimize this subject to W2 this. There is a absolute mod function. We can that way, relax that with W2T, a new variable which is defined like this: minus T. This is always a positive say continuous number, positive number, minus T less than minus tap new this. So that is the formulation. So now we have load, three types of load: constant impedance, constant power, and constant current. In a constant impedance load, constant impedance load is V square by something, right? Because the V square, so we have defined V square to a new variable, so that is captured. Similarly for Q. But constant power load does not have a function of V at all. So that's also not a problem. But when you have a constant current load, that is normally, 1V. But that 1V does not exist because we have redefined a new variable called V square. So if we keep the 1V for the constant power, constant current load, then that this U becomes square root of U. So again, you lose that the convexity or the linearity. How do we then deal with the constant current load and also the forecast error of the load? So we assume the forecast error of the load to be Gaussian in nature. So these are our auxiliary variable, V square, U, and all. So voltage dependent load is this: loads, Jeep and exponential, static nonlinear load, alpha P, alpha Z, this. So now we have voltage and nodal injection, say Jeep, and exponential and constant P. So this is the power versus the magnitude of the voltage. So they look like this, right? Constant power is the voltage, constant the Jeep, constant impedance, constant current, constant power, that is the green one, the blue one, and the exponential model is the red one. So what we now do, the voltage dependence in convex solver, how V square is U, so that is available. So this Z and P is alpha P plus alpha Z V square. But then current, constant current is not captured. So now let's see how we can do. So this is typically a binomial series. 1 plus x delta is this. So think about the V. V is V0 plus delta V. So that's how you express V. The power network normal operating condition, if I put this V to the power of n, is 1 plus delta V to the power of n, which is 1 plus n into delta V. Okay. For a very small delta V, we can approximate this like this, because then if you go with n square, etc., then what happens? That becomes delta V square. Now, because delta V is small, so you can truncate that. So good approximation due to delta V very, very, very less than 1, and eta of delta V is also very, very less than 1. So that's a good approximation. Why? So normally under normal operating condition, your voltage is 1 per unit, and anything that is varying is by delta V. So now let's see how we can then do that in the Jeep load: alpha P, alpha Z V square, alpha I V. So this one you can, because this is V0 plus delta V to the power of that. So you can express this as that. Okay. This V it's a 1 now. So 1 plus that what you saw there, delta V, 1 plus delta V. So that's how you can have that one delta V, you can split into delta V by 2 and delta V by 2. So you can absorb it here. Here is also that V, the 1 plus delta V square. So you can, half of that you can absorb as a constant impedance load, and half of that you can absorb as a constant power load. That is alpha I by 2. Okay, we know that coefficient. So that's how it does. And similarly for exponential load also it can be done. So then once you have accommodated it, then you make that as an alpha 1p and alpha 1z. So then for a Jeep model, it's taken care of. For exponential model also it is like this. If you put this again beta, you will find that you are getting something like this 1 minus beta by 2 and p0 beta by 2 v square. So you see that? So this is constant power and this is constant current. So irrespective of the value of the beta, if I have a beta is equal to 1, so that's a constant current load, isn't it? Fully constant current load. So beta 1 means this is half into constant power and half into constant impedance. So this is that again formulation. So there is another approach, that is the binomial, this approximation method. And there is also least residual method where you can estimate like the desired voltage range. You have lots of samples. Say I have a sample from 0.95 to 1.05, many samples, and I can put it there. And these are my actual load model. Say P alpha, etc. I do not actually know all this alpha and beta for the exponential. So then what I do, I put each of those value of the voltage and come with this matrix V into this. So then for each of these voltage, if I can put, I can get the value of the power here. And then I put the power as P. So then that becomes what? That V into that is equal to P. And I'm trying to approximate this, okay, here. So that P plus some residual, that I have some error in that, some residual. So the idea is to find out when residual is 0, then this would be V inverse into P, but there is a residual. So what you do, idea is to find alpha P hat, alpha Z hat, that would more or less match that P, and if the matching error is R, that is this, and we minimize that R. Okay, so that is the LRI minimizes the residual. That comes from your normal equation solution. Then this is, you can see V transpose V inverse, V transpose P. Why it is coming? How it is coming? What you need to do, multiply both sides by V transpose. So V transpose, because this is a tall matrix, so V transpose V is V transpose P into V transpose R. Now V transpose V is a square matrix. So then you can take the inversion of that. So V transpose V invert into V transpose V invert into V transpose into P. That is your alpha P, where you are minimizing that R. Okay. So that this. So that the Jeep loads a special case for this V1 square, etc. alpha this. So we can put that for as a W. So then what happens? This now becomes this W matrix, because V transpose V into the W into that here. So now we need to see that the whole thing V transpose V inverse V transpose is a matrix called C, and then that for Jeep load. So this is C, and we need to find out C, which is that. And then after all these things, this comes as function of CP and then CZ, constant power and constant impedance part. And this expression for CPV is this V, etc., and CPZ is this. So the V is that, and then when you take V suffix 2 means this is the point element wise multiplication, V dot V. Similarly, then V3 is again V dot into V, and V4 is actually again V dot into this element product into V3, like that. So then we put that into this. So Jeep model is red, normal operating range, binomial approximation, that is the black curve. Now you see that when you are very close to 1 per unit voltage, the red and the black curves are very close to each other. That is what was that binomial approximation method. We had 1 plus delta V to the power of eta. We approximated that to be 1 plus eta into delta V. Okay. So whenever your network is operating around normal operating condition, then binomial approximation method is really good to find out that, alpha p and alpha z hat. But whenever you are away from this, so then is the residual LRM, okay? Least residual method. You could see here the green with the G. You can see the green is coming very close to the red here, right? Here and also here. And for exponential, similarly, when you are very close to the normal voltage, your BAM is better. And when you are outside of that, then your LRM is better. So that means we now have a method to absorb that constant impedance, constant current part of the load into the apportioning that into constant power and constant impedance. So then now let's go to the scenario enforcement algorithm. So we generate loads of scenarios, operation complexity, scenario optimization, intelligently select only a handful of best scenario, faster convergence, guarantee all operation scenarios satisfied, best performance, etc., etc. So now let's see how is this. We start our optimization process. Initialize solution scenario set by best case scenario. Perform VOLT-VAR control. So do a deterministic on a best case. That VOLT-VAR control give you your control variable set point would be transformer tap position, capacitor bank positions, and also some other ABC, which I'll tell you that they connect the reactive power of the DG with the real power, some relationship. So you, with this value, best case, you form your Y bus and do the LU factorization of the Y bus. So it becomes I is equal to YV. So find the V. So once you find that V, and let's see, what happens there. Now here, what you do, you have forecast of the error. Forecast of the error is in the power, the real power. So you put a different value of the real power and we generate many scenarios because you have an error of with a standard deviation of 5%, 10%. This with that sigma, you can generate million number of scenarios. And once you get that scenario, that's a P and Q. So then you could express that as, that P as VI. So I would be that P by V, or that is that here you're doing actually I is equal to YV. So essentially what you do, you calculate the value of the voltage. Okay, I is equal to YV, and then that I is P by V. So that's, and then V goes there. So that's how you can get that. So once you get the voltage that you have got the value of the voltage, use each of those scenario to pass through that, okay, and see what is the value of your voltage. Now, is it between 95% to 100.5%? If it is within that, then put that into a basket. If it is not, then leave that in another basket. So then at the end of all those millions of scenarios where you have done this check with this known Y bus based on this, because Y bus would be impacted by this transformer tap position and this position. So then you see that, okay, we have violated, say out of 100,000 scenarios, we have violated about 10,000 scenarios where voltages are not within the limit. So then we need to go for scenario reduction. So how we do that? Like perform VOLT-VAR control basic schedule, check the violated scenarios, and take all those violated scenarios, then pick any one of those violated scenario and set a kind of a distance, a Euclidean distance with respect to that. So, or in other words, take any violated scenario and get the distance of that with respect to any another scenario. So suppose you have 10,000 violated scenario, choose any one of them and take the difference with respect to that with all the 9,999 scenario and generate that distance and order them. And once you have ordered them from small to high, and then put a cutoff that, okay, if the distance is more than this threshold, I am not going to treat that as within my cluster. So with that threshold value, if those scenarios which are within that threshold of equilibrium distance, I say that, okay, these are all my in one cluster. And like that, I can have many clusters. How many clusters you have, that depends on how small your threshold is. If your threshold is very small, you have many clusters. And from each of those clusters, you take one representative value. So, and then that becomes the reduced set of violated scenario. So you reduce that set of violated scenario based on that distance and add those violated scenario as a constraint to your objective, convex programming where P and Q, that expression. So then run the scenario based chance constant. So then put all the scenario as a constant that it becomes larger. So then once you run that, then again you get some kind of new A, B, C, TJ, BJ. With that, you go back to your reformulation of the Y-bar, and then again do the power flow solution, current injection based power flow solution, and then go over all those, say, 10,000 violated scenario, but you only considered, say, about 10 cluster. So 10 representation. So you have discarded 9,990, but you have to now check whether those discarded 990 is within this. So in that way, what you will find that now out of those 9,990 or 10,000, you may find about 100 scenarios are now violated because you now have a different value of ABC, and do the same process and again go and check. And after some time, you will see that all the scenarios you are able to exhaust that way. So this is the two-stage optimization. Okay, so that process. So how it all works? In the beginning, you have a capacitor and OLTC setting, and you have got that scenario run, and don't change that OLTC and setting. Keep that fixed, and then this is the Q of the reactive power output of the DG as a function of its real power. That if this can be expressed by this kind of rule, A PDG square B PDG C. So if you see that if A and B are 0, you have a constant reactive power. So you won't be able to do any kind of optimization. If you take A0 and C0, then you see that you have Q is B into PDG. That's a constant power factor scenario, right? Q by P is B. That's a constant power factor. So now having A, B, C, then you can have a nonlinear relationship. So then throughout the, say, optimization window, say every half an hour if you do, or every 1 hour if you do. So in the beginning of the hour, whatever the B and tap position you have got, keep it there. And then what happens is, let me see, then you go like this. So then I have this voltage violation probability is the fraction of the total node voltage. The deterministic case, you have, this is the 3 network, and this side is the standard deviation. And you see that on the deterministic case, if you find something for the best case, and then you try how many voltage have been violated, you see that this is the VVP, number of violated scenario. Maximum can be NB into a number of Monte Carlo. So you see that it is growing, percentage is 18%. And then standard deviation, and then the chance constant is the green. You see that it is not going up. This is for one network, UKGDS 95, and this is for 123, and this is for 190. So the chance constant has got very less percentage of the violation. And what is this axis? As you increase the standard deviation of the error, 0.1, 0.15, 0.2, 0.25. That one. So, and then the switching count discount controller, because we have W1 and W2 in that objective function. If we put actually W2 to be 0, that means we don't pay attention to transformer tab movement, this. So then you have almost 24 cases, number of switching. Whereas if you put some priority, 25%, this is less. When you put 75% priority, this is less. So that epigraph programming with W1 and W2 weighted optimization gives you a balance between the loss minimization and tap this thing. And similarly, the losses, what you see here, the forecast error in this way, and how the loss, this is the chance constant loss minus the deterministic case divided by deterministic case. So that is the conservative index. Normally, the loss minimization, the chance constant would be, would be say the loss actually, not minimization. The value of the loss would be higher than the value of the loss in deterministic case because you have a suboptimal solution. So for all the other cases, you have to get the average of that. So PLCC would be the average of that, and this is this. So that's why it's a positive quantity, and you see that it's as you increase this standard deviation, you see that your conservative index is also going up. So this is the nodal uncertainty need to be considered in the VBC scheme, more important than ever. Chance constant VBC framework can be efficiently solved through the scenario enforcement algorithm, shows robust performance. Two-stage control structure introduced to give additional recourse opportunity. Decision voltage dependent loads model was needed to improve the convex solver, and we done that. So this is this only here. And Firdos was the researcher here. Firdos, are you in the attendance? No, Firdos is not in the attendance. I do also other areas that Sai has already said to me. So this is my current group. So these are all the people who supported us. So do you have any comment or question? Let me see the time. At 3 o'clock, I exactly have another meeting. So maybe maximum I can do one question answer. Otherwise, I need to go to that meeting. If you have question, write the question for to Sai, and then later on I would answer those questions. Okay, guys. Let me.
Thank you, Professor. So, guys, if you have any questions, you can type in the chat. Otherwise, it's already like just 1 minute ahead of your other meeting, so we can end the meeting now.
Okay. So thank you for attending to this. I really appreciate. So, okay. So I need to go to the other meeting. Yeah, and send the questions. We'll do this.
All right. Okay, guys, thank you so much. If you have any questions, you can type here or send email. You can get replaced from Professor. So that's all.